Hello, GCC 152 students. Today we're going to be looking at buffer solutions. We're going to be looking at what a buffer solution is. We'll look at the definition for a buffer. We'll also look at combinations of different solutions to determine if they're buffer solutions or not. And we're going to find out how a buffer works and what buffer capacity means. A buffer solution is a solution that will resist changes in pH when we add a small amount of acid or base. It will try to keep the pH constant. Buffers are very important. They actually are used to control the pH of blood and other biological fluids, and they're very important in industry and also in the medical field. And with looking at the components in a buffer solution will either consist of a weak acid combined with its conjugate base. So something like acetic acid would be a weak acid. Sodium acetate would be a salt that contains its conjugate base. Conjugate base of acetic acid is the acetate ion. And the other possible buffer solution would be a weak base and a salt containing its conjugate acid. So something like ammonia. Ammonia is a weak base. Ammonium chloride is a salt that contains its conjugate acid, the ammonium ion. Now we're going to take a look at a combination of different solutions to determine if they fit this criteria of a buffer solution. Do they contain a weak acid and its conjugate base, or a weak base and its conjugate acid? So we're going to start off here. Let me see if I can find a drawing tool here. With looking at HF and NAF. So for HF, we know that HF, actually that one's not very good. HF here, we know that that is a weak acid. So this would be considered to be a weak acid. And when we look at the fluoride ion, this would be the F negative ion. This would be its conjugate base. So here we do have a weak acid. We have the F negative ion, which is its conjugate base. Now, what about for ammonia? We know that ammonia is one of the weak bases that you're expected to know. But when we look at the salt here, and we see that this contains the ammonium ion. So the ammonium ion would be considered to be the conjugate acid of this weak base. Now, what about when we have KOH? Well, KOH is not considered to be a weak acid or a weak base, clearly. It's considered to be a strong base. So here we know we have a strong base. So we have a strong base, and we actually have KF, which would be a basic salt. So this does not fit the criteria that we're looking for. Now, if we have acetic acid, we know acetic acid again, this would be considered to be a weak acid, and lithium acetate is a salt that contains its conjugate base. So this would also fit that criteria. I'm going to go ahead and put up the answers on these because you can kind of see the trend that they're following here. Then here we see that we have a strong acid that's not a buffer solution, strong acid and a salt containing the nitrate ion. Then we have a strong base and a neutral salt. So clearly that's also not a buffer solution. So the ones that were considered to be buffer solutions, we had either a weak acid and its conjugate base, which would be considered to be a weakly basic ion, or a weak base, such as ammonia, and its conjugate acid, ammonium. Now we're going to take a look at how a buffer solution works. As we mentioned before, our buffer solution contains our two important components, a weak acid and its conjugate base. And we will see that the weak acid component of our buffer will react with added strong base. So if we add a strong base, it will supply hydroxide ions. And the hydroxide ions will then react with our weak acid to produce its conjugate base and water. So this is a neutralization reaction. When we have an acid and a base forming water plus a salt, that's considered to be a neutralization reaction. This is the net ionic neutralization reaction. Now, for the second possible reaction, we'll see that the basic component of the buffer, the acetate ion, will react with added strong acid. And the strong acid solution will provide hydronium ions. Remember that a strong acid will ionize completely to produce H+ ions, which in aqueous solution become hydronium ions, and the hydronium ions then react with our basic ion to produce our weak acid solution in water. This is also, again, we have an acid-base neutralization reaction. Buffer capacity is the amount of acid or base that our buffer is able to neutralize before the pH changes significantly. Buffers, there's a couple of important points that will affect the buffer capacity. First of all, we want to make sure when we prepare a buffer that we're preparing a buffer that had about the same amount of the weak acid and conjugate base, or weak base and its conjugate acid. So we want to make sure that it's roughly a 1-to-1 ratio, but as long as we're within a 10-to-1 ratio, the buffer should still work. So we want to make sure that the ratio falls between 0.1 to 10 to be within that 10-to-1 ratio. And also, we'll see that the buffer capacity will be a lot larger if we have higher concentrations of our weak acid and conjugate base present. In our next video, we'll be taking a look at the Henderson Hub equation, and we'll take a look at how we can use that to calculate the pH of a buffer solution, where the equation is pH equals pKa, that's the negative log of the Ka value, plus the log of the conjugate base over our weak acid concentrations. Now, keep in mind, you do not want to use this equation for any other combination. You don't want to use it for like a strong acid, strong base combination, for example. You have to make sure that when you're using this equation that you're plugging in the concentration, the concentration, or you can plug in the number of moles for the weak acid, and similarly you can plug in the concentration of its conjugate base or the number of moles for the conjugate base, because we know that molarity is moles over liters, so the liter terms would actually cancel out. So that's why you're able to plug in moles directly into this equation. And also in our next video, we'll be taking a look in more detail at the difference between the ICE versus change tables. The ICE tables, the ICE tables, are used when we have a weak acid or a weak base equilibrium reaction, but we're going to be using change tables for neutralization reactions. And again, we'll take a look at that in a little more detail in our next video.